In this next chapter, we are going to look at integration. Before we can actually start talking about integration, we need to discuss a few things. So the first is this notion of the differential. If y is a function of x and it's differentiable, delta x is some change in x. So given a point and we find some small change away from that point, then dy equaling f prime of x delta x is the differential. And if we kind of look at what this means pictorially, okay, if I have some function of x and I pick a particular point, so there's my f of x naught, and again I look at some distance away from that point, so let's call this x1, where this distance is delta x. Then if I look at the tangent line from this point, and I compare the points on both the function and the tangent line that are delta x units away, I get an f of x1, and over here I'll get this point which is on my tangent line. Okay. So this tangent line is f prime of x, and if I look at this point over here, this is going to be f prime of x1. Okay. This differential is basically telling us the difference between these 2 points, meaning the original point, notice f of x naught and f prime of x naught in this case are exactly the same. So the difference between the point on the curve and the point delta x units away on the tangent line, this is our dy. If we actually look at delta y, so notice delta x is our change in x. Delta y is the change in the y values. So here, if I'm looking at this point out here and the original point, this would be delta y. And the whole notion of this dy, or this differential, is that if I'm looking at tangent lines, my tangent line for small delta x's will basically approximate my curve. And what that means is my delta y and my dy will be approximately the same for small delta x's. Obviously, the bigger my delta x, the bigger this change is going to be. Okay. Now, for this course, we're not going to use a lot of the applications that come along with differentials, but we are going to use the differential in our notation for our integration. And again, it tells us basically this change between the function and the derivative at some small distance away. So our next definition is the antiderivative. The antiderivative of a function f is a function, I'm going to call it capital F, such that capital F prime is equal to f, meaning little f is the derivative of big F. Okay? Or in our differential notation, it says that d capital F is little f of x dx. Again, dx and delta x are the same. The distance away from x naught to our point on either the curve or the derivative is the same distance. Okay? So let's consider some functions. Let's look at f of x being x squared plus 7, g of x equaling x squared minus 3, and h of x equaling x squared. Okay? And one of the things to notice is if I look at the derivative in each case, here, using my power rule, I'm going to get a 2x. Here for g of x, again I'm going to get 2x. And if I look at h prime of x, I'm also going to get 2x. Okay? And so what this is saying is, even though I have slightly different functions, and the slightly comes from the fact that they differ by a constant, all of the derivatives for these are the same. So if I'm trying to get an antiderivative, meaning if I start with these derivative functions and try to go backwards, the base function is going to be the same in each case, but again, the antiderivative is going to differ by a constant. Okay? And so we use the integral notation to denote the antiderivative. So again, there's this differential notation which says I'm looking at a derivative, but if I want to show that I want to take an antiderivative, I'm going to use what we call the integral notation. And this funny looking sign here is what we call our integral sign. So this is saying the integral of f of x dx is capital F of x plus some constant, which we're just going to call c. And this is true if and only if capital F prime of x is the derivative for f of x. Okay? And again, we said that in our definition of the antiderivative. So let's look at some basic properties of integration. So in this table, let's look back at what we did for derivation, so finding the derivative, and let's look at the corresponding property for integration. And what you're going to see again is that integrating is just undoing the derivative. Okay? So here let's look at a couple of the properties we had before. Okay? So we had, for constants, if I wanted to take the derivative of a constant, we knew that the derivative was just going to be 0. Okay? So going backwards from that, basically I took away the value and made it go down 1. Here I'm going to increase it by 1. So instead of going to 0, when I integrate, I'm going to get a k times my variable of integration. And here again, don't forget your constant of integration. That constant just means that I could have some number attached to the function at the end of the integration. Okay? If I look at x to the n, for our derivative, we said we're going to bring the power down front, multiply by x, and then subtract 1 from the exponent. Okay? For integration, we're going to do the opposite. So instead of subtracting 1 from the exponent, I'm going to add 1 to the exponent, and instead of multiplying by the old exponent, I'm going to divide by the new exponent. Again, I'm going to have some constant of integration at the end of that. Now, for x to the -1, for derivation, this was included in the x to the n property. But notice here, so let me write that up, this would have been -1 x to the -2. So it would follow that same property that we had above. But here, if I tried that for integration, notice if n is -1, I'm going to get 0 in the denominator. Okay? And so for this one, we actually have to think backwards a little bit further. When we got further along in our derivatives, we saw that when we took the derivative of a natural log, we ended up with a 1 over x. And so for this one, if I'm looking at x to the -1, and I want to integrate it, I'm going to end up with the natural log of x. Here we have to be careful because x has to be positive, where it doesn't over here. So we need to include absolute values. And again, our constant of integration. Okay. Our nicest function of all, e to the x when we took the derivative. We saw we just got e to the x. Same thing is true if I take the integral. If I start with e to the x and I integrate that, again I'm just going to get e to the x plus my constant of integration. Okay. For the last 2 or 3, however you're going to look at this, functions, we had our coefficient property for derivatives. So if I had some k times my function, remember here we could just say it was k times the derivative of the function. Okay. Or if you like, we could think of that as k times f prime of x. Okay. For integration, the property works very similarly. If I have some coefficient times my function, I can basically move that coefficient out front and then take the integral of the function. So here, I'm going to move the k out front, take the integral of my f of x with respect to x. And again, remember I need my differential on here. Now notice in this property I didn't add a plus c, and that's because I haven't taken the antiderivative yet. Once I take that antiderivative and get rid of the integral sign, that's when my plus c will get added. Okay. And then for the last properties, our plus and minus, this is what we used for most all of our polynomials. This was basically our derivative of f plus or minus the derivative of g. Likewise, for integration, the property works very similarly. If I have an f plus a g and I want to integrate, it's going to be the integral of f with respect to x plus or minus the integral of g with respect to x. Okay. So there are our basic integral properties. And just like with derivatives, there are other properties out there. So if you remember our product, quotient, chain rule, we had logarithm properties, implicit. There are similar types of things for integration. So once we get into more complicated functions, we will have other properties that we're going to use to integrate functions. Okay. So let's look at some examples of integration. Okay. So in this case, we've just got a few of them. We're going to use our basic properties to find the antiderivatives. So in this first one, the integral of 5x dx, if we look, this is basically just a coefficient times our x. X here we can think of as x to the first power. So here, I'm going to bring that 5 out front, and I'm basically looking at the integral of x dx. When I apply my power property, this is x to the first, so I'm going to get an x squared, so adding 1 to my exponent over 2 plus c. And again, we always want to simplify, so here I can think of this as 5 halves x squared plus c. Okay. In my next one, 3x squared dx. This is again a power property with a coefficient. So again, I can start by pulling the coefficient out front and then apply my power property. So here I'm going to add 1 to the exponent, divide by that new exponent, plus my constant of integration. And again, once I'm here, I'm going to simplify to get my antiderivative. Okay. In these last two examples, we're using some of the other properties there. So in this next one, I still have a coefficient times x, but now I've also got an e to the x and a difference. Okay. So here we can separate this out. This is the integral of 2 times the integral of x dx minus the integral of e to the x dx. Okay. Again, applying my power property, I can see I'm going to get an x squared over 2. So that 2 will cancel out. I'm left with an x squared plus c minus antiderivative of e to the x plus c. Okay. And notice in this one, I didn't write out all the steps, but I'm still doing the same thing. My power property is still being used, but I've just canceled things a little without writing them down. And because both of these started as a single one, and they're both going to have a constant of integration, when I add those constants together, it's still going to be a constant. So I only have to put one c in the answer. Okay. In this last one, I'm looking at the integral of 4 over x dx. And if it helps, this one I can think of as the integral of 4x to the negative 1 dx. So here I can see that I'm going to use my x to the negative 1 property, which says that my antiderivative is an ln of x. The only difference is I have that 4 out front. So here again I'm going to bring the 4 out front. Now I'll apply my property. And again, don't forget my constant of integration. So let's look at a couple more examples of basic integration. In the last few examples we looked at, all of our integrals were set up using just our basic properties. But just like in derivatives, they are not always going to be set up so that you can see right away what the property is that you're going to need to use. In some cases, you're going to have to algebraically manipulate the function so that it looks like the basic properties. So in this first example, we can see x squared times the quantity x plus 2/3 dx. So here, again, it almost looks like a product, but again, we haven't talked about a product rule for integration. And so here, the first thing I'm going to want to do is get rid of the multiplication by distributing so that I have all of the terms in the form of a polynomial. So here, I'm going to take and multiply through by the x squared. And now I can see this is just a sum of terms with some powers and coefficients. So here, using my power property, x cubed is going to look like x to the 4th over 4. And 2/3 x squared is going to look like 2/3 times x cubed over 3. Again, once I've taken my antiderivative, I'll get rid of the integral sign and add my constant of integration. Okay. Again, cleaning this up, looks like a 1/4 x to the 4th plus a 2/9 x cubed plus my constant of integration. In this next example, this one does almost look like some of our basic properties. So we can see with the power of the negative 3 in the second term, I can see my power property very easily. In the first term, the root is what makes it a little bit more manipulation needed in order to take the antiderivative. So here, again, I'm going to start by rewriting the function. This is going to be 2x to the 4/5 plus 3x to the negative 3 taken with respect to x. And so again, I've got some coefficients and powers. Taking my antiderivative, I'm going to add 1 to the exponent, divide by that new exponent. Same thing over here. Add 1 to the exponent, divide by the new exponent. And again, don't forget the constant of integration. Simplifying. So here again, I've got a fraction underneath the fraction bar, so I'm going to invert and multiply. So this is going to look like 10/9 x to the 9/5. Over here, that minus sign will come out, so minus 3/2 x to the negative 2 plus c. Now this one, we started with some negative exponents, so we can end with them. But again, in some cases, if it says to simplify, we're going to run a rewrite that. So it looks like 10/9 x to the 9/5 minus 3 over 2x squared plus c. Okay. Either of these would be acceptable answers. Okay. In our last example, We have a combination of this first one we looked at and also some division. So here again, I don't have a product or a quotient rule, at least not yet, and so I've got to determine how to get the antiderivative. And again, in this case, it's going to require some rewriting. So on the top here, I can start by, again, getting rid of the multiplication by multiplying out. So we'll get a 2x squared minus an x plus a 6x minus 3 all over 6. With that, I can now separate these terms. We'll go ahead and combine the middle ones, but I can separate over the denominator. So I'm going to have the integral of 1/3 x squared. We've got a 5x over 6, so plus 5/6 x, and then minus 3 over 6, or a half. And again, with the sums or differences, I can do each term individually. So pulling the 1/3 out, antiderivative of x squared, I'm using my power rule again, so x to the 3rd over 3, plus the 5 over 6. I'm going to take that x, add 1 to the exponent over that new exponent, and then for the 1/2, which is a constant, I'm going to add in an x. Again, don't forget the constant of integration. From there, same thing, go ahead and combine. So we've got a 1/9 x to the 3rd plus 5/12 x squared minus a 1/2 x plus c.